All right, today we're diving into something wild. We are tackling a problem that mathematicians for centuries have basically labeled unsolvable. But there's a new, pretty controversial theorem out there that claims to have cracked it. So we're going to break down exactly how it claims to work and what it could mean for, well, the future of algebra.
So let me just throw this out there to start. What if the problems we call unsolvable are only unsolvable because of the tools we've been using? What if the problem itself isn't the issue, but our approach has been? It's a heck of a question.
Okay, first step, let's meet the villain of our story, a particularly nasty-looking polynomial equation.
We've all seen this, right? You look at it and you instantly, without even thinking, know that x equals 3. It's clean, it's simple, most importantly, it's exact. This is our baseline. This is what a solvable problem looks like.
And then you get this, an 8th degree polynomial. Yeah, finding x here is not so obvious. This is the kind of equation that makes even seasoned mathematicians take a deep breath.
Now, with a monster like this, we can totally throw it at a computer and get an answer. But here's the catch. That answer is almost always an approximation. You know, a super long decimal that's close enough. The problem is, close enough can hide tiny rounding errors. It's not the perfect, exact answer that mathematicians are really after.
So, you might be wondering, what's the big deal? Why isn't close enough actually good enough? And why do our trusted classical methods just fall flat when they come face to face with a beast like this?
This really gets to the heart of it. On one hand, you have the classical methods, which often lead to these numerical approximations. They get you in the ballpark, but they might have those little hidden errors. On the other hand, you have the goal, kind of the holy grail of algebra, a symbolic solution. That means a clean, precise, 100% correct answer. No rounding, no close enough, just the truth.
And you know, there's a really good historical reason why this is so hard. A cornerstone of modern algebra called Abel's theorem basically built a giant wall. It proved that once you get past a 4th degree polynomial, there's just no universal formula, like the quadratic formula, that uses things like square roots to find the exact answer. For centuries, that wall has seemed pretty much unbreakable.
But what if you didn't have to break through the wall? What if you could just walk around it entirely? This is where the hero of our story comes in, a totally new way of thinking called Ezouidi's theorem. So this theorem comes in with a really, really bold claim. It says it can find the precise symbolic answer for any polynomial, no matter how high its degree is. And it does this using a completely different process that just sidesteps approximation altogether. The way the source material describes it, the method is almost like a recipe. You start with the numbers from your original equation, you apply this special recursive formula to them, and that process gives you a brand new set of values. And those new values have the power to transform that monster equation into something incredibly simple. Okay, that all sounds great in theory, right? But talk is cheap. Let's actually see how this whole process plays out on that crazy 8th degree polynomial we met a minute ago. So the method kicks off by taking all those original numbers from the equation and feeding them through its special recursive formula. The whole goal right now is to calculate a new symbolic coefficient, which we're going to call S0. And after all that number crunching, the result that pops out for this very first new coefficient is a perfect, clean 0. No decimals, no approximations, just 0.
Interesting, right? But is that just a fluke? Well, the process is repeated for the next coefficient in line, S1, and the result is, well, it's just as surprising.
It's another perfect 0. Okay, now a real pattern is starting to emerge here. It feels like this method is uncovering some kind of deep, hidden structure inside the equation. And this isn't a coincidence. According to the source, this remarkable pattern just keeps going. The process continues for all 8 of the symbolic coefficients that are needed for this equation. And every single one of them from 0 all the way to S7 calculates out to be exactly 0. It's like all that complexity from the original equation just evaporated.
So what was the point of all that? Well, this is the magic trick. By calculating those 0 coefficients, the theorem allows us to transform our huge, intimidating polynomial into this. X to the 8th power equals 0. An equation so simple you can solve it just by looking at it.
Now hold on. There's one final step in the method. That simplified equation, x to the 8th equals 0, isn't the final answer itself, but it's the key that unlocks it. The theorem uses this incredibly simple form to derive the actual root of the original monster equation, and the paper claims that root is a single exact value, x equals -3. And that little note about multiplicity of 8, that just means that for this specific equation, this one root is the answer 8 times over. It's a precise symbolic answer exactly as promised.
That is a pretty stunning result for one equation. But let's zoom out. What are the bigger implications here if this method actually holds up? What kind of new power does it claim to give us?
This comparison really highlights the difference in philosophy. You see, with classical methods, as the degree of an equation grows, the complexity just explodes. This theorem claims that has no effect. Classical methods are built on the idea of radicals, square roots, cube roots. This theorem doesn't even use them. It's presented as an entirely different way of looking at the problem.
So it all boils down to these incredible powers the theorem claims to have. Universality, meaning it should work for any polynomial. Robustness, it can handle tricky cases with repeated roots. And the big one, independence from radicals, which allows it to just walk right past those classical limitations set down by Abel's theorem.
And that leaves us with this final massive question. We've seen the claims, we've seen the demonstration on one seriously challenging example. Could this really be a key that unlocks a whole new universe of problems we thought were impossible? Or is it a fascinating, but maybe specific case that just forces us to rethink what the word unsolvable even means in the first place? The source makes its case, and, well, it leaves the rest of the world to figure out what comes next.